So welcome to video problem 5, where we consider a parallel plate capacitor and we derive its capacitance and stored electrostatic energy. So here we see our parallel plate capacitor. We have the upper plate up here with the total charge Q and the lower plate down here with the total charge minus Q. The surface area of both conducting plates is designated with symbol A, and they are separated by a distance d. The space in between is filled with a simple material with this permittivity epsilon shown here, so that we have this simple relationship between the d field and the E field in the capacitor. We will assume that the plate separation distance d is much smaller than the side length of our parallel plate capacitor, and this is equivalent to assuming infinitely large plates. In this case, our total charge will be uniformly distributed so that the surface charge density on the top plate will be given by the expression here, and it will have the negative sign and the same magnitude on the lower plate. We illustrate this by showing this distribution of charges on top and bottom plates, and this uniform distribution of charge will also lead to uniform electric fields in the dielectric and also the D fields. Here we have included the field lines for the electric field, and we also neglect fringing fields so that the field only exists inside of the dielectric between our conducting plates. So we have zero fields everywhere outside. So we are using the standard procedure from the book, where we have assumed charges Q on our conductors. We will then determine the D field. When we know the D field, we will determine the E field. When we know the E field, we will determine the potential difference or the voltage between the two conductors. And then finally we will determine the capacitance as the assumed charge divided with the determined potential difference. So here we see our parallel plate capacitor again. We have now introduced a y-axis as shown here, so that our lower plate is located at y equal to 0 and the upper plate is located at y equal to d. This is the standard formula for getting the capacitance, where V naught is the voltage from our positively charged conductor to the negatively charged conductor. In this assignment, we will use the boundary conditions for the normal component of the D field to get the D field inside of the capacitor. D1 is the field in medium 1, D2 is the field in medium 2, and this unit vector points from medium 2 to medium 1. This is the free surface charge density at an interface between these two materials. To this end, we can introduce the designation of medium 1 as being our dielectric inside of the capacitor, and medium 2 can actually be the space outside of the capacitor, but it can also be this conducting plate. This doesn't matter because this will represent fields D2, which are 0 in either cases. With this introduced designations, our unit vector will obviously point in the negative y direction, and our field D1 will be actually also pointing in the negative y direction, and it will have this magnitude d. Because of what I just said, the D2 field will obviously be equal to 0, and when we plug these ingredients in this boundary condition, this is the result that we get. On the right hand side, we have the free surface charge density, which is the total charge divided with the surface area. Here we have this unit vector, which dotted with that unit vector will give you unity, so you can actually see what the magnitude of the D field is. In the vector form, this will be the field at the upper plate, but because this field is uniform throughout the dielectric, it will also represent the D field inside the dielectric. Knowing the D field, it's very easy to get the E field because we are talking about simple material inside of the dielectric. So by simply dividing the D field with the permittivity, we arrive at this expression for the electric field intensity, and we can then integrate this electric field intensity from the positively charged conductor to the negatively charged conductor. This is the electric field, and this is our dl element in this particular way. This is a straightforward integration because we are essentially integrating a constant and we are multiplying it with the length of our integration path, which is nothing else than this symbol d that you can see here. Now we know the voltage between the conductors, so we can divide the assumed Q with the calculated voltage and arrive at this expression for the parallel plate capacitance. We can see that it doesn't depend on Q, it doesn't depend on V0, but it depends on the material properties, here exemplified in terms of this permittivity epsilon, and also on the geometry of our capacitor, which is the surface area of your conductors, and also the separation distance between those conductors. So we have now completed the derivation of the capacitance for our parallel plate capacitor, and we are also now in position, or we would actually like to determine the stored energy inside of this parallel plate capacitor. This is the general equation for calculating the stored energy. So it is 1/2 volume integral of E dot d, and here the D field is known from the previous slide, and also the E field. So we can dot these two vectors to get this result here, which you can see is constant in the dielectric material. We have introduced this x, y, z coordinate system as shown here, so our volume integral is essentially an integral along x, along y, and along z. And because our integrand is constant, we will essentially multiply this integrand with the volume of our dielectric material, which is the surface area times the separation distance. So this energy is very easily calculated to be given by the expression here, or in another way expressed in this particular manner. So this was a very easy, you can say, determination of the electrostatic energy for a parallel plate capacitor. Now that we know the energy, we can use the energy, as you know, for an alternative determination of the capacitance for our parallel plate capacitor. This is the standard formula that will link the energy and the capacitance. So from this one we can isolate the capacitance and plug in the energy that we have determined here to arrive at the same final result that we have derived on the previous slide. So we have now completed all our tasks, and here you can see the derived results for the capacitance and electrostatic energy for a parallel plate capacitor. As usual, we have a few tasks for you. Here we would like you to check the units for the capacitance and the electrostatic energy, and you have seen that we have used the boundary condition for the D field to determine the D field at the upper plate of our parallel plate capacitor, and by using uniformity of the D field, this was then the field in any point in the dielectric material. But instead of using the boundary conditions, we could have used Gauss law to get the D field, and this is a task for you to do. So thank you very much for your attention.